For this problem, you're solving for the force that is experienced by a moving particle in a magnetic field. In order to figure out the force, you're going to use the equation that is Q times V cross B. If you'd like to find the magnitude, you can do Q times V times B times sine of the angle between the velocity and the magnetic field. Now you're going to input the values. Since it is a positive particle, you know that it's 1.6 times 10 to the negative 19th coulombs times the velocity, which is 4 times 10 to the 5th meters per second, times the magnetic field, which is going to be 0.2 teslas, times the sine of the angle between them, sine of 30 degrees. When you evaluate this, you're going to get 6.4 times 10 to the negative 15th Tesla meters. Now, in order to figure out the direction of this force, you're going to take your fingers and have them aligned with V, and then pull down to B. This is going to give you an into the page force vector. So you know that it's 6.4 times 10 to the negative 15th newtons into the page. For this one, you're trying to solve for the charge of a particle that is moving in a magnetic field. Since the equation that we know is F is equal to QV cross B, and V cross B is not going to get you a zero number. You know that the only thing left to give you a zero force is going to be Q, because the particle is not experiencing a force. So that must mean that Q of the particle is zero, making this a neutral particle.
For this part, we need to solve for the magnitude of the magnetic field. To do this, we're going to use the equation B equals mv over qr. The next step is just to plug in all the numbers that we know. After we solve this, we get our final answer to be negative 0.011 teslas. Now we have to find the direction of the field. To do this, we would use the right-hand rule. So if we use the top point as our point, the velocity would be to the left, the force would be down, and that would give us a magnetic field direction going into the page. But since we got a negative value for our the magnitude of the magnetic field, that means we would flip it, and therefore it's out of the page. So the final answer is 0.011 teslas for the magnitude and out of the page for the direction.
We were given an electron moving to the right with an electric field uniformly acting upward. So we know that the force caused by the electric field is equal to the charge times the electric field. We set the force of the electric field equal to the force of the magnetic field. We use the equation that magnetic force is equal to the charge times the cross product of velocity and magnetic field. The magnitude of the magnetic force is equal to the charge times the velocity times the magnetic field times sine of the angle between the velocity and the magnetic field. So we use the equations for electric force and magnetic force and set them equal to each other. So the charge times the electric field is equal to the charge times the velocity times the magnetic field times sine alpha. And from that, we got the magnetic field is equal to the electric field over the velocity sine alpha. So we plugged in the numbers, and eventually we got the magnetic field is equal to 0.05 teslas. And for the direction, we use the cross product. So using our right-hand rule, we know the velocity was pointing to the right, the force was pointing upwards, so that means that the magnetic field is pointing into the page or into the board. But because it's a negative charge, that means it's flipped, so it's pointing outwards.